Welcome to the Audiophile Bot video. This presentation will give you a look at what the Audiophile Bot is capable of and let you in on a little of what went into making her tick. This project is brought to you by David Whalen, Damon Tregear, David Ryan, and Eddie McCrucian. This project turns a remote control tank into a low-frequency signal-seeking robot. It uses sensors and code to control the vehicle, as we learned to do in California State University Sacramento's Electrical and Electronic Engineering 174 Intro to Microprocessors course. We have removed the innards from a remote control tank and replaced the circuitry with our own. An Arduino Micro was used to control the tank. The tank has a lot of functionality. 1. It uses a microphone sweep on a servo to tell in what direction a specific signal frequency is. 2. That data will be used to control the tank to drive in the direction of the signal source. 3. An infrared sensor's data will be used to stop the tank from running into obstacles. When stopped, it will reassess the direction of the signal source and repeat. 4. We'll show the signal amplitude the tank is tracking remotely via radio frequency on a liquid crystal display via another Arduino Uno. The tank was a great success, but after extensive testing and revisions, the Arduino Micro and sweeping motor burned out as the project deadline arrived. The project was moved to a prototype build, which features all the sensor systems of the tank. That prototype is what we'll be looking at as we explore the functionalities of the Audiophile Bot. A servo is used to control a microphone in a 180-degree range, taking 5 samples as it turns. It would stop at every 45 degrees and take 7,000 samples. The Arduino would compare the samples to find the maximum amplitude. The turret would then turn in that direction. This data would be used to guide the tread motors in the direction of the source. Originally, the microphone would take samples as the servo rotated, but the electrical noise from the servo running would affect the readings. We fixed this by turning the servo on and off to sample using a pin on the microcontroller and a transistor. The IR sensor also produced noise, so we routed the power for it through the same transistor. We put in a low-pass filter to reduce the noise and to capture only low frequencies for the robot to follow. Our target range is sub 100 Hz. Thanks to the low-pass filter, we achieve this handily. The maximum amplitude reading is 512 on the Arduino, which corresponds to the voltage level coming from the microphone. With a very high-amplitude low-frequency signal, the amplitude reaches up to 450. The typical range is from 20 to 80. 2 separate DC motors control the left and right treads of the tank. These are connected to PWM pins on the Arduino Micro. Typically, this is not an ideal way to gain control of DC motors because the digital pins on the Arduino Micro can only output 40 milliamps of current, and most DC motors require a couple of amps to drive them. Luckily, the DC motors for this tank were capable of functioning around 20 milliamps, allowing digital PWM pins to be used to control the tank's movement. It was discovered, however, that more current was needed to actually rotate the mechanical gears within the tank to spin the treads in the desired direction. To resolve this issue, a dual H-bridge was implemented into the circuitry. Once the maximum amplitude signal is found, the body of the tank would rotate to the position of the turret, which signified where the signal was found. To rotate the tank in the desired direction, analog right functions were used to control the direction and speed of the tank treads. For example, if the maximum amplitude signal was detected to the left of the body of the tank, the right tread DC motor would be controlled to move forward, and the left tread DC motor would be controlled to move backwards until the desired position was reached. The motors would be controlled to move the tank forward until another audio detection sweep occurs. While the tank is moving, an IR sensor attached to the front of the body of the tank analyzes the immediate forward surroundings within 10 to 80 centimeters. Due to the nonlinear characteristics of the IR sensor's voltage output versus the detected distance, the distance conversion equation found in the IR dist function was used to output the correct centimeter distance in the Arduino serial monitor. When an object is detected to be impeding the tank's path, the tread's DC motors are brought to a halt. Once stopped, the motors are put into reverse until the tank is sufficiently distant from the impeding object, such that it can conduct another audio detection sweep and repeat the preceding process. A radio frequency transmitter along with a receiver were utilized to send microphone amplitude data from the tank to another Arduino Uno. The virtual wire library was used on the transmitter and receiver Arduinos for easier use of the RF sensors. This library allows for transferring characters instead of individual bits. The library parses the bits into characters for you, so you don't have to translate ASCII into binary before sending. Since the library takes an array of characters, raw sample data cannot be transmitted directly. The integer value must first be turned into a string variable. Then the string is parted into individual characters and put into an array to be sent out. The RF components use the timers which are associated with PWM, pulse width modulation, pins, resulting in conflict with running motors and servos. To work around this, we also use the Servo Timer 2 library, which uses another timer that does not conflict. The transmitter and receiver transmit data at 433 MHz. Its maximum transmission rate is 5 kilobits a second, with a maximum character package size of 27. The code must transmit message length and the message for it to be understood on the receiving end. We transformed the string into an integer using the ATOI message function. We put that data onto an LCD using the Arduino liquidcrystal.h library. The code clears the LCD, sets the start position of the printed message, displays a line describing the data, then on the second line, updates the received data whenever it is updated. We ran into many problems that we needed to bypass and solve. Input noise to the signal sampling pin caused by the servo and IR sensor was fixed by powering the components on and off with a transistor. A low-pass filter for the signal was used to reduce ambient noise and to detect a specific range of low frequencies. The virtual wire library, servo library, and PWM pins conflicted with timers used, for which various fixes were applied. We learned that an H-bridge is required to power motors with PWM since the microcontroller is unable to supply the current needed through the pins that run the motors. Originally, we planned to implement digital filtering, which would have used less power, but learned that this was a more complex task than we knew, and so with time constraints in mind, we used a passive analog filter instead. This project challenged each member to think beyond current knowledge and look for solutions to problems never encountered before. The biggest problem we came across was the Arduino Micro in the tank dying. Our only recourse was to prototype the project, as there wasn't enough time to order new parts and rebuild the tank. The audiophile bot was a huge learning experience for the whole team, even though we were unable to use it to conquer the world as we had intended.